Welcome back. Let's do this example. A hot air balloon is moving upwards at a constant unknown speed. Right. Question A. Is the hot air balloon in free fall? Choose from yes or no and then give a reason for your answer. Right. Is the hot air balloon in free fall? If you check, this balloon is moving upwards at a constant unknown speed. We know that if an object is on free fall, it falls under the influence of the gravitational force or gravitational acceleration. So it means if it is on a free fall, it accelerates downwards at 9.8 meters per square second. But this one is at constant velocity. So it means it's not accelerating. Okay, so it means the acceleration here is 0. So this is not on free fall. That's one reason you can write. You can also say that there are other forces which are acting on this balloon, or stating that it is in constant velocity. Okay, so these are some of the reasons you can have here. So there are other forces acting on the balloon. Acceleration is not 9.8 meters per square second. Downwards, actually, acceleration is 0 because it's on constant speed. So any one of those, you can write them. Okay, let's go to question B. When the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram alongside. Another small stone B is dropped 5 seconds later from the balloon while the balloon is still moving upwards at a constant velocity. Stone A strikes the ground at a speed of 62.68 meters per second. Ignore air resistance. Now we need to calculate the speed of the hot air balloon. How do we do that? Right. So we have the stone which is on the hot air balloon. When the stone is leaving the balloon, its initial velocity is equal to that of the air balloon. Okay. So calculating the initial velocity of the stone is just the same as calculating what? The velocity of the balloon. Okay. So now what do we have? We have, let's take upwards as positive and starting point as 0. So it means we take this as our reference point. We have the initial velocity, that's what we're looking for. The initial velocity, we're looking for initial velocity. And then we have the final velocity. We're taking this, we're taking upwards as positive, so the final velocity is going to be negative 62.68 meters per second. Right, what else do we have? We have acceleration. We're taking upwards as positive, so acceleration is negative 9.8 meters per second squared. By the time it hits the ground here, by the time it hits the ground, what will be the displacement? You see, we're taking the starting point as our 0 reference. So now it means displacement will be negative 200. Okay, 200 is below the starting point. We're taking upwards as positive. So that displacement is negative 200 meters. And then we look for the equation of motion that we can use. We check your equations of motion. The best one to use here, which has initial velocity, final velocity, acceleration, and displacement, is Vf squared is equal to Vi squared plus 2a delta 1. Then we substitute. Our final velocity is negative 62.68 squared is equal to the initial velocity squared plus 2 times negative 9.8, and then our displacement is negative 200, right? And then now what we can do, we can isolate this. It becomes final velocity. Right, we're going to subtract this from this. Okay, we just transpose the whole thing, bring it to the left. It becomes this bracket minus this whole product here. Okay, and then we square root both sides because we want initial velocity, so we're going to square root both sides. So it becomes square root of negative 62.68 squared minus 2 negative 9.8 then minus 200. Okay, so we just do that, and then this will give us our initial velocity, okay, which is 2.963511,431. So we took upwards as positive, so it means initial velocity is 2.96 meters per second. Okay, that's the initial velocity. If we take downwards as positive, the calculation will be just the same, but now initial velocity, we're still looking for it, but our final velocity now is going to be positive if we take downwards as positive, right? There are many options of doing these calculations. Remember that we may do our calculations differently and get these answers. So 62.68 meters per second. And then acceleration, downwards is positive, it means it's going to be 9.8, positive 9.8 meters per square seconds. And then displacement now, taking downwards is positive, so it means displacement is 200 meters. Okay, all right. So the calculations are just the same. We use the same equation of motion. Vf squared is equal to Vi squared plus 2a delta y. Then substitute 62.68 squared is equal to Vi squared plus 2, then 9.8, then 200, like that. And then what you do, we subtract this product from this, and then we square root both sides. So V initial is equal to the square root of 62.68 minus 2, 9.8, then 200. Okay, then put this in the calculator. It will give you your initial velocity, which is negative 2963511,431, because we took downwards as positive and the balloon is moving upwards. So it means initially the stone is moving upwards with the balloon. So that's why I'm getting negative here. So you can say, therefore, Vi is equal to 2.96 meters per second upwards. That's B1. Right, let's do B2. Now we have our initial velocity of the stone. Let's do B2. Right, we read the information. We can read it again. But it says calculate the time it takes stone A to strike the ground. So what we have here, we have the initial velocity. We just calculated our initial velocity, isn't it? It's now 2.96 meters per second. And then we have our acceleration, and then we have the final velocity. We're given the final velocity, and then we can find time. Okay, right, let's start by taking upwards as positive. If we take upwards as positive, then our initial velocity is 2.96 meters per second. And then our final velocity, if we take upwards as positive, is negative 62.68 meters per second. Right, and then acceleration is equal to negative 9.8 meters per square seconds. And then now we're going to use our equation of motion. Final velocity is equal to initial velocity plus a times delta t. Then we substitute negative 62.68 is equal to the initial velocity 2.96, then plus our acceleration negative 9.8 delta t. Right, we can subtract both sides. We get negative 65.64 is equal to negative 9.8 delta t. Then divide both sides by negative 9.8. You get negative 9.8 delta t. And divide both sides by negative 9.8. What do you get? Okay, that delta t is equal to 6.697959,184. So meaning that our time is 6.70 seconds. Let's take downwards as positive. If we take downwards as positive, then the initial velocity, because initially the balloon is moving upwards with the stone, so it's going to be negative 2.96 meters per second. Then the final velocity now is going to be positive 62.68 meters per second. And then acceleration also is positive 9.8 meters per square second. And then we use our formula. Final velocity is equal to the initial velocity plus a delta t, right? So we substitute, we have 62.68 is equal to negative 2.96 plus 9.8 times delta t. Add 2.96 on both sides of the equation, we get 65.64 is equal to 9.8 delta t. Then divide by 9.8 on both sides of the equation, we get that delta t is equal to 6.7 seconds, just like this one. Alright, we're going to do question B3. Please remember this. Our initial velocity is 2.96. Our final velocity, we got it. What was it? Final velocity was, or we're given the final velocity. And then we just got time. Which is 6.7 seconds. Okay, right. So remember this as we go to question B3. Right, let's read the information again before we answer this question. When the balloon is 200 meters above the ground, a small stone is dropped from the balloon. That is stone A. See the diagram alongside. And then another small stone B is dropped 5 seconds later from the balloon while the balloon is still moving upwards at a constant velocity. So it means stone A is released, and then after that, after 5 seconds, stone B will be released. Right, stone A strikes the ground at a speed of 62.68 meters per second. Ignore air resistance. And then we're asked to calculate the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. Right, let's look at this. So we're saying that stone A will take 6.7 seconds to strike the ground. Then stone B is released 5 seconds later. Or stone B is released 5 seconds after stone A is released. Now, so when stone A hits the ground, for how many seconds is stone B traveled? When stone A hits the ground, for how many seconds is stone B traveled? It means stone B is only traveled for 1.7 seconds, isn't it? For stone B. Okay, let's say time for stone B. It will be 6.7 minus 5, which is 1.7 seconds. So it means by the time stone A hits the ground, stone B is only traveled for 1.7 seconds. Okay, let's go back to the question. Calculate the distance between hot air balloon and stone B at the instant when stone A strikes the ground. Right, let's take upwards as positive first. So what do we have here? We have the initial velocity of stone B. It's just the same as that of what? Of stone A, because for both stone A and stone B, their initial velocity is the same as the velocity of the balloon. So the initial velocity here is 2.96 meters per second. And then we set time. We just did time here, so it's 1.7 seconds. And then acceleration when you take upwards as positive is negative 9.8 meters per square second. Right. Now we want to find the distance traveled by stone B. We have initial velocity, we have time, we have acceleration. We want the one that is also going to give us displacement. So which equation is that? We have delta y is equal to initial velocity times delta t plus half a t squared. Okay, we just substitute into the formula. So delta y is equal to 2.96, then 1.7 plus half acceleration negative 9.8 and then 1,7 squared. And then what you get, delta y is equal to negative 9,129. So displacement will be negative 9,13 meters. That's if we take upwards as positive. Okay, so it means now displacement, calculate the distance between the hot air balloon and the stone B. So the distance will be 9,13 meters. Let's take downwards as positive. Our initial velocity will be negative 2,96, because initially these things are moving upwards. And then time, we have our 1,7 seconds, and then acceleration, if it's moving downwards, is 9,8 meters per second, per square seconds. Then we're looking for displacement. Okay, so we just substitute into the same formula, this one, delta y is equal to initial velocity times time plus half a t squared. So displacement will be negative 2,96 times 1,7 plus 1 over 2, 9,8, and then 1,7 squared. So we're taking downwards as positive. So displacement will be 9,13 after rounding off, just the same as this one. So now the distance between the hot air balloon and stone B is 9,13 meters. Right, let's look at the last question. See, when the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram alongside. Another small stone B is dropped 5 seconds later from the balloon while balloon is still moving upwards at constant velocity. Right? Stone A strikes the ground at a speed of 62,68 meters per second. Ignore air resistance. On the same set of axes, draw position time graphs of both hot air balloon and stone A from the moment the stone is dropped until it strikes the ground. Use the ground as 0. Please take note of this. We're now using the ground as 0 reference. Label the graphs balloon and A for stone A. Right, I'm going to show you two diagrams, but you don't need to draw both of them. You just choose one. Okay, I'll show you the one when we take upwards as positive, and then the other one we take downwards as positive. But if you're answering these questions, you just choose one option. Okay, even if you're doing your calculations, you don't need to do both calculations for upwards as positive and downwards as positive. No, just choose one and you answer. Don't waste time. This is the position time graph. So our vertical axis will be our displacement in meters, and then here will be time in seconds. Same here, displacement in meters, and then time in seconds. So we're drawing position time graph. Let's start with the balloon. It is moving at a constant velocity. Remember, the gradient of the position time graph gives us the velocity. And then if it's constant velocity like this, it means it must be a straight line. It means the position time graph must be a straight line because the velocity is constant, is not changing. But what is happening to the displacement from the ground? It is moving away from the ground. So it means the displacement is increasing. Right, we're taking upwards as positive. So it will start at 200 meters. That is 200 meters. And then it will start going up like this. It's a straight line, should be a straight line. Okay, and then that is the balloon. But what about the stone? It will start by going up first, because remember, it is going up with the balloon, then it is dropped. So it will start at 200 and then goes up a bit, and then after a few seconds it goes down. And then we know that this one will be, the time taken to get here will be 6,7 seconds. Right, so this is A for stone A. Right, if we take downwards as positive, then what is the displacement? Our ground is our 0 reference. And then we're taking downwards as positive. It means at this point, displacement is negative. But remember, we said that if we take downwards as positive, the displacement below the reference point is positive and displacement above the reference point is negative. And then if we take upwards as positive, displacement above the reference point is positive and displacement below the reference point is negative. Please take note of that. So here, our displacement is above the reference point and we're taking downwards as positive, so it's going to be negative. So that's negative 200 meters, and then it moves away from the reference point, so it becomes more negative. That is for the balloon. And then the stone A, it will start by going up. So as it goes up, the displacement is becoming more negative. And then turns and moves towards the zero reference to the ground. So this is for stone A. And then the time is 6.7 seconds. We calculated this in question B2. The time is 6.7 seconds. Okay, so this is how we're supposed to do this question. Let's meet when we do example 2.